Hashtag the universe, when measurements break reality. Imagine the moment when everything you believe to be solid suddenly crumbles before your eyes. When the foundation of your understanding of the world turns out to be built on sand. This is precisely what's happening right now in cosmology, the science of the universe. And this isn't just another discovery. This is a revolution. Scientists measured the size of the universe twice and got different answers. How is this possible? How can the universe have two different sizes, two different ages, two different expansion rates? This isn't a measurement error. This isn't a technical glitch. This is something bigger. Something that forces us to reconsider everything we know about reality. Welcome to the age of the cosmological crisis. In the quiet offices of observatories, beneath the domes of telescopes, in laboratories where supercomputers calculate galaxy trajectories day and night, something incredible is unfolding there. A drama that could rewrite all of physics. Cosmologists measure the universe. They do this constantly, for decades, with increasing precision. And now, in recent years, they've encountered a paradox that becomes more frightening with each new measurement. The universe is expanding. We've known this since 1929, when Edwin Hubble first noticed that distant galaxies are moving away from us. But here's the question: how fast? At what rate is the fabric of spacetime inflating? One method gives us the number 73. Another, 67. Does the difference seem small? Only 6 units. But in cosmology, these 6 units are an abyss. A chasm. The difference between a universe we understand and a universe that obeys laws unknown to us. This number is called the Hubble constant. It's measured in kilometers per second per megaparsec. It sounds complicated, but the meaning is simple: it's the speed at which the space between galaxies increases. The Hubble constant isn't just a number. It's the key to the history of the universe. To its age. To its fate. This number tells us where we came from and where we're going. It determines how much time has passed since the Big Bang. It predicts how long the universe will exist before it plunges into eternal darkness or tears itself apart with dark energy. And this number doesn't add up. Imagine you're trying to determine the age of a tree using 2 methods. One method says, the tree is 100 years old. Another claims, the tree is 115. And both methods are absolutely accurate. Both have been verified. Both cannot be wrong. What does this mean? That time flows differently for different parts of the tree. That there are 2 realities, superimposed on one another. This is exactly the paradox cosmologists face. Here's the first method. We look at nearby galaxies, those in our cosmic neighborhood, at distances of several hundred million light-years. We find special stars in them called Cepheids. These stars pulsate at a certain frequency, and this frequency is related to their brightness. Knowing the true brightness and comparing it with the apparent brightness, we can calculate the distance. Then we measure how fast these galaxies are moving away from us. And we get the Hubble constant. The result, 73 kilometers per second per megaparsec. This number was obtained by the Hubble telescope. It's been verified by the James Webb Space Telescope, the most powerful instrument humanity has ever created for observing the cosmos. Webb sees the universe in incredible detail, in high definition, leaving almost no room for error. And it confirms, 73. But there's also a second method. We don't look at nearby galaxies, but at the most ancient radiation in the universe, the cosmic microwave background. This is light that was born 380,000 years after the Big Bang, when the universe first became transparent. This light carries within it the imprint of the early universe, its structure, its composition, its initial conditions. The Planck Space Telescope mapped this radiation with phenomenal accuracy. Then cosmologists took the Standard Model of Cosmology, our best theory about how the universe is structured, and ran it forward 13.8 billion years. They got a prediction about what the Hubble constant should be today. The result, 67.4 kilometers per second per megaparsec. 2 methods. 2 answers. Both accurate. Both independently verified. And they don't match. There was a time, not so long ago, just 20 years ago, when cosmology seemed like the triumph of human reason. We built a model of the universe, and it worked. It explained everything, from the formation of galaxies to the distribution of matter in space. From the evolution of stars to the fate of spacetime itself. This model is called Lambda-CDM. Lambda-cold dark matter. It sounds boring and technical, but behind this name lies the greatest achievement of human thought. This is our cosmological Bible. Our map of reality. According to this model, the universe consists of several ingredients. Ordinary matter, atoms from which stars, planets, and we ourselves are made, constitutes only 5% of the entire contents of the cosmos. 5%. Everything else is dark matter and dark energy. Dark matter is an invisible substance that doesn't emit light but creates gravity. It holds galaxies together, forms the cosmic web, determines the large-scale structure of the universe. It accounts for about 27% of the cosmos. And the rest, 68%, is dark energy. A mysterious force that causes the universe to expand faster and faster. It acts like anti-gravity, tearing the fabric of space from within. This model worked flawlessly. It predicted observations. It explained data. It was elegant and simple. We thought we understood the universe. We were wrong. Think of yourself as a cartographer in medieval times. You draw a map of the world based on travelers' tales. The map turns out beautiful, internally consistent. All cities on it are connected by roads. All rivers flow into seas. Everything makes sense. And then the first navigator who circumnavigated the earth arrives. And his stories don't match your map. The distances are wrong. The continents aren't there. What seemed like the center of the world turns out to be a distant periphery. What do? Declare the navigator a liar? Or admit that your map was just an approximation, a good approximation, but not the truth? This is exactly the situation cosmologists find themselves in. Their map of the universe, the Standard Model, worked perfectly as long as we looked at certain things in a certain way. But once we changed the angle of view, used different instruments, measured different parameters, the map stopped corresponding to the territory. The universe we observe here and now is expanding faster than it should according to our model of the early universe. This isn't just a discrepancy. It's a signal. The universe is telling us, you're missing something. There's a gap in your picture of reality. There's something you don't see. Try another way. Imagine a mighty oak. You look at its seed, a small acorn, and, knowing the laws of biology, calculate what the tree should be like in 100 years. You account for all factors: rainfall, soil quality, temperature, competition with other plants. 100 years later you return. And you see the tree. But it's not what it should have been according to your calculations. It's taller. The crown is wider. The trunk is thicker. What happened? Was there an underground river you didn't know about? A special symbiosis with fungi? Or perhaps the laws of growth themselves aren't what you thought? This is exactly what's happening with the universe. We look at its seed, the cosmic microwave background, the imprint of the early universe. We apply our best laws of physics to grow from this seed the modern universe. And we get one tree. But when we look around us, when we measure the real universe here and now, we see a different tree. Similar, but not the same. Somewhere between the seed and the tree, between the beginning and the present, something happened that we didn't account for. To understand the scale of the problem, we need to understand the scale of the instruments we're using. The Hubble Space Telescope has been operating in orbit for over 30 years. It's a legend. An icon of space science. Its images adorn textbooks. Inspire generations, change our perception of the universe. Hubble sees far. Very far. It looks at galaxies whose light has been traveling to us for millions and billions of years. To look into space is to look into the past. Light isn't instantaneous. It travels at a speed of 300,000 kilometers per second, and even at such an unimaginable speed, it takes eons to cross cosmic expanses. When we see a galaxy a billion light-years away, we see it as it was a billion years ago. We're looking into the past. The telescope is a time machine, aimed backward. And so, for decades, with the patience of monks and the precision of watchmakers, astronomers used Hubble to build the cosmic distance ladder. Step by step, star by star, galaxy by galaxy, they measured the universe. First nearby stars, whose distances can be measured directly using parallax, how their position changes as Earth moves around the Sun. Then Cepheids, pulsating stars whose brightness and pulsation period are linked by an iron law. Then supernovae, exploding stars that briefly become brighter than entire galaxies and are visible at enormous distances. Each rung of this ladder is calibrated against the previous one. An error on the lower rung propagates upward, amplifying with each step. Therefore, precision is critically important. Therefore, each measurement is checked and rechecked countless times. And Hubble was accurate. Surprisingly accurate for an instrument launched in 1990. But doubts always remained. What if a systematic error crept in somewhere? What if stars in distant galaxies don't behave quite like nearby ones? What if dust and gas distort their light in ways we haven't accounted for? These doubts evaporated in 2021 when the James Webb Telescope entered orbit. James Webb isn't just a more powerful version of Hubble. It's a qualitatively different instrument. Its mirror is 7 times larger. It sees in the infrared range, in light invisible to the human eye, but which penetrates dust clouds and brings us signals from the most distant corners of the universe. Webb sees galaxies that were born when the universe was only a few 100 million years old. It observes the formation of the first stars, the first black holes, the first structures in space. It looks at an epoch Hubble could only dream of. And when Webb was pointed at the same Cepheids that Hubble observed, something surprising happened. Or, more precisely, didn't happen. No exposure occurred. No error was discovered. Webb confirmed Hubble's measurements with frightening accuracy. Webb's resolution is so much higher that it sees individual stars where Hubble saw a blurred spot. It can distinguish a Cepheid from neighboring stars, even if they seem merged in Hubble images. It looks through cosmic dust like an X-ray through flesh. And it says, Hubble was right. The Hubble constant really equals 73. This should have been a triumph. A confirmation. An affirmation of our understanding. Instead, it became a death knell for the standard model of cosmology. Because if Hubble is right, if Webb confirms it, if there's no error, then the problem isn't in the measurements. The problem is in reality itself. To understand the second method of measuring the Hubble constant, we need to return to the beginning. To the very beginning. 13.8 billion years ago there was nothing. No time, no space, no matter, no energy. There was only a singularity, a point of infinite density and infinite temperature, where all the laws of physics we know ceased to work. And then the Big Bang occurred. Not an explosion in space, but an explosion of space itself. The universe began to expand, cool, evolve. More changes happened in the first second than in all the subsequent billions of years. For the first moments, the universe was opaque, a seething ocean of plasma where photons couldn't travel even microscopic distances, constantly colliding with particles. It was like trying to see through thick fog, where every ray of light scatters after a millimeter. But 380,000 years after the Big Bang, something magical happened. The universe cooled enough for electrons and protons to combine into hydrogen atoms. The plasma turned into gas. The fog cleared. And light was able to travel freely through space for the first time. This light travels still. It fills the entire universe. It comes to us from all directions, like the faint afterglow of an ancient fire. We call it the cosmic microwave background radiation. This is the most ancient light in the universe. This is the echo of the Big Bang. And in this echo is encoded information about the early universe, its temperature, its density, its composition, the tiniest fluctuations that later grew into galaxies and galaxy clusters. In 2009, the European Space Agency launched the Planck Space Observatory. Its mission was simple and grand at the same time, to create the most accurate map of the cosmic microwave background. Planck didn't look at stars and galaxies. It looked at the emptiness between them, at the faint, almost indistinguishable glow that fills all of space. It measured the temperature of this radiation with precision down to millionths of a degree. And here's what it saw: the universe in infancy was surprisingly uniform, but not quite. There were tiny inhomogeneities, regions slightly hotter and slightly colder than average. These fluctuations amounted to only hundred thousandths of a degree, but they were critically important. Because these fluctuations were the seeds of galaxies. Regions with slightly higher density attracted matter through gravity. They grew, condensed, turned into proto-galaxies, then into galaxies, into galaxy clusters, into the magnificent cosmic web we see today. Planck measured these fluctuations with incredible precision. It compiled a map of the early universe, a kind of baby photo of the cosmos at the age of 380,000 years. And this map tells a story. From the size and distribution of these fluctuations, cosmologists can derive the fundamental parameters of the universe: how much ordinary matter it contains, how much dark matter, how much dark energy, what the geometry of space is. Having these parameters, cosmologists do the following. They take the standard model of cosmology, a set of equations describing how the universe evolves, and run it forward in time. Imagine this as a computer simulation. You set the initial conditions. The universe at age 380,000 years looks like this. Then you press the play button and watch as the virtual universe evolves. Gravity pulls matter into clumps. The first stars ignite. Galaxies form, collide, merge. Dark energy accelerates the expansion of space. You fast forward 13.8 billion years and stop the simulation at today. And you look at what kind of universe resulted. In particular, you look at the rate of its expansion. At the Hubble constant. And the standard model, run from Planck data, gives the answer, 67.4 kilometers per second per megaparsec. This is a forecast. A prediction of what the modern universe should be like if we correctly understand physics. Now compare this with direct measurements of the universe we live in, 73 kilometers per second per megaparsec. A difference of 8%. That doesn't sound catastrophic. But in cosmology, it's an abyss. It's as if you predicted a person should be 170 centimeters tall, but they turned out to be 184 centimeters. Something is clearly wrong. Either our initial conditions are incorrect, or the physics of evolution is incorrect, or our measurements of the modern universe are incorrect. Webb ruled out the third option. The measurements are accurate. This isn't an observational error. The first two possibilities remain. And both are frightening. Because they mean we don't understand the universe as well as we thought. 10 years ago this was called the Hubble tension. An unpleasant discrepancy, yes. A puzzle, undoubtedly. But it seemed solvable. Just tweak the models a bit, refine the measurements a little, and everything would fall into place. It didn't. 5 years ago the tension intensified. New measurements confirmed the discrepancy. Precision increased. Statistical significance reached a level where it could no longer be ignored. 3 years ago, some scientists began speaking not of tension, but of crisis. The Hubble constant remains the #1 unsolved problem in cosmology. And now, in 2024 to 2025, after the James Webb Telescope confirmed Hubble's measurements, after all conceivable sources of error were ruled out, after dozens of independent studies came to the same conclusion, now the crisis is entering a new phase. Physics is breaking. Before our eyes. In real time. What does this mean? If the universe is expanding faster than the standard model predicts, then there's something accelerating this expansion. Something we haven't accounted for. Something invisible but incredibly powerful. Physicists propose various options. Each sounds like a plot from a science fiction novel, but each is seriously discussed at scientific conferences. Perhaps there's early dark energy, a special form of energy that existed in the first moments after the Big Bang and gave the universe an additional push. This push wasn't accounted for in the standard model, but we're observing its consequences now. Or maybe dark energy isn't constant. The standard model assumes that the density of dark energy is the same at all times. But what if it changes? What if dark energy today is stronger than it was billions of years ago? This would explain why the modern universe is expanding faster than expected. Some theorists go even further. They propose the existence of completely new particles or fields. Exotic matter. Strange energy. A fifth fundamental force of nature besides gravity, electromagnetism, and the two nuclear forces. There are even proposals for a mirror universe, a parallel world that interacts with ours only through gravity. The gravitational effects of this mirror universe could influence the expansion of our spacetime in ways we don't account for. Or maybe the problem is even deeper. Maybe Einstein's general theory of relativity itself needs modification on cosmological scales. This theory works flawlessly in the solar system, predicts black holes and gravitational waves, but perhaps it fails when it comes to scales of billions of light-years. Each of these ideas is a revolution. Each requires rewriting physics textbooks. Each means we live in a stranger, more complex, more amazing universe than we thought. Imagine a ship sailing in thick fog. The captain has two navigation systems. One is a compass and a map compiled at the beginning of the journey. The other is direct observations of stars and shores. The compass says, "We are here." The stars say, "We are there." The discrepancy is small, but enough that the difference between them means either calm sailing or collision with rocks. The captain rechecks the compass. It works perfectly. Check star observations. They're accurate. Consults the map. The map is detailed and verified by generations of navigators. And yet the systems don't agree. What to do? Trust the compass and map, and possibly crash. Or trust the stars, and abandon everything the ancestors knew. This is the situation modern cosmology finds itself in. We must choose, trust the model of the early universe or direct measurements of the modern one. And any choice means admitting that somewhere we're fundamentally wrong. It's time to talk about what measuring the universe actually means. Because even this concept itself is full of pitfalls. When we talk about the size of the universe, we usually mean the observable universe. This is the part of the cosmos whose light has had time to reach us in the 13.8 billion years since the Big Bang. It would seem simple. If the universe is 13.8 billion years old, and light travels at a speed of 300,000 kilometers per second, then the observable universe should have a radius of 13.8 billion light-years. The diameter, accordingly, would be about 27.6 billion light-years. But no. Reality is more complex. The thing is, space is expanding. Galaxies whose light we see were once much closer. During the billions of years their light flew to us, these galaxies moved even farther away. Imagine shooting an arrow at a moving target. The arrow flies for a second. During this second, the target manages to move away. The arrow hits the place where the target was a second ago, but the target itself is now in a different place. The same with galaxies and light. We see a galaxy where it was billions of years ago. But now it's much farther. When cosmologists account for the expansion of space, they get the following: the observable universe has a radius of about 46.5 billion light-years. Its diameter is approximately 93 billion light-years. This figure is so enormous that the mind refuses to perceive it. 93 billion light-years. Light, traveling at a speed of 300,000 kilometers per second, would have to fly for 93 billion years to cross the observable universe. In this sphere with a diameter of 93 billion light-years, there are, by estimates, about 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star can have planets. Multiply these numbers. Try to comprehend them. You cannot. The human brain didn't evolve to grasp such scales. And now, the most important thing. The most dizzying. The most frightening. The observable universe isn't the entire universe. It's only the part we can see. Only the part whose light has had time to reach us. What's beyond its boundaries? We don't know. By definition, we cannot know. If light from some region hasn't reached us yet, we cannot observe it. It may be there, but for us it doesn't exist. Not in a practical sense. Is there more space beyond the horizon of the observable universe, more galaxies, more stars? Almost certainly yes. There's no reason to believe that the universe magically ends exactly at the boundary of what we can see. That would be an incredible coincidence, as if we stood exactly at the center of all that exists. Most likely, the universe continues far beyond the observable part. But how far? Some studies, based on statistical analysis of galaxy distribution and properties of cosmic space, suggest that the full universe is at least 250 times larger than the observable part. Think about this. 250 times larger. The observable universe with its trillions of galaxies is just a tiny bubble in an ocean of more extensive reality. If this is so, then the diameter of the full universe is more than 20,000 billion light-years. 20 trillion light-years. This number loses all meaning. This isn't a scale. This is an abstraction. But there's another possibility, even more dizzying. The shape of the universe depends on its geometry. General relativity allows three variants. The universe can be closed, like the surface of a sphere. In that case, if you flew in one direction long enough, you would eventually return to the starting point. Such a universe is finite but has no edge, just as Earth's surface is finite, but you'll never reach its edge, constantly finding yourself again and again on the same sphere. The universe can be open, like a saddle or negatively curved surface. Such a universe is infinite. Or the universe can be flat, like an infinite sheet of paper. In this case, parallel lines remain parallel forever, and space extends to infinity in all directions. Measurements of the cosmic microwave background conducted by Planck indicate that the universe is flat with very high precision. The curvature of space, if it exists at all, is so small that we cannot detect it. If the universe is truly flat, it's most likely infinite. Infinite. Think about this word. This means that somewhere, beyond the limits of the observable universe, at distances we can never measure, there exists an infinite number of galaxies. An infinite number of stars. An infinite number of planets. In an infinite universe, everything that's possible happens. Somewhere there exists an exact copy of the solar system. Somewhere there's an exact copy of Earth where you're reading the exact same article. Moreover, there are infinitely many such copies. In an infinite universe, probability becomes necessity. If something has a non-zero probability of happening, it will happen. Moreover, it will happen an infinite number of times. This isn't science fiction. This is a mathematical consequence of infinity. Let's return to the Hubble constant. To this cursed number that refuses to converge. 73 kilometers per second per megaparsec. This is local measurement. What we see around us. What Hubble and Webb observed directly. 67.4 kilometers per second per megaparsec. This is prediction based on the early universe. What should be if our physics is correct? The difference is 5.6 kilometers per second per MPC. Only 5.6. But these 5.5 units are the abyss between understanding and ignorance. What does this number mean practically? Let's imagine. Take two galaxies located at a distance of 1 megaparsec, that's about 3.26 million light-years, from each other. According to the Hubble constant, the space between them expands at a rate of 67 to 73 kilometers per second. This difference affects our estimates of the universe's age. If the Hubble constant equals 73, the universe is younger. If 67, older. The difference amounts to several hundred million years. This may seem insignificant against the backdrop of 13.8 billion, but for cosmologists it's critical. Because the age of the universe is connected to everything else, when the first stars formed, when the first galaxies appeared, how much time life had to arise. In science there are two things, theory and observations. Theory predicts what should happen. Observations show what actually happens. When theory and observations coincide, we're happy. We think we understand the world. When they diverge, real science begins. Usually, when theory and observations don't match, we assume the observations are wrong. Because observing is difficult. Measuring is complex. Instruments are imperfect. Systematic errors lurk at every step. But sometimes, very rarely, it turns out that the observations are correct and the theory needs revision. The last time this happened was at the beginning of the 20th century. Then observations of planetary motion, the precession of Mercury's orbit, didn't match the predictions of Newtonian gravity. The discrepancy was tiny. But it was real. Einstein explained this inconsistency by creating general relativity, a revolutionary theory that replaced Newtonian gravity with the curvature of spacetime. Now we're in a similar situation. We have a discrepancy between theory and observations. And everything indicates that the observations are right. Does this mean we need a new revolution in physics? A new Einstein? A new theory that will explain both old observations and new ones, and eliminate the Hubble tension? Perhaps. Cosmologists around the world are working on this. They propose modifications to the Standard Model. They invent new particles and fields. They reconsider the nature of dark energy and dark matter. Maybe in 10 years we'll remember the Hubble tension as the moment when new physics was born. As the crack that grew and shattered the old paradigm, freeing space for something greater. Or maybe the solution will turn out simpler. Maybe we're missing some subtlety in measurements. Some effect that seems insignificant but accumulates. Maybe in a year an article will appear that explains everything, and we'll breathe a sigh of relief. But with each new study, with each new confirmation of the discrepancy, this possibility becomes less likely. The data are rebelling against theory. And the data are winning. To truly appreciate the size of the universe, let's descend from the heights of cosmology down to familiar scales, then climb back up. This is a journey through the scales of existence. Let's start with a human. You. Me. About 2 meters tall. Step up, Earth. Diameter about 12,750 kilometers. To walk around it along the equator, you need to cover 40,000 kilometers. By car, that's about a month of continuous driving. Step up, distance to the moon. 384,000 kilometers. Light reaches it in 1.3 seconds. A car traveling at 100 kilometers per hour without stops would get there in 160 days. Step up, the Sun diameter 1.4 million kilometers. More than 1 million Earths could fit inside it. The distance from Earth to the Sun is 150 million kilometers, or 8 light minutes. Step up, the Solar System. If we count to Neptune's orbit, its diameter is about 60 astronomical units, or 9 billion kilometers. Light crosses it in 8 hours. Voyager 1, the fastest man-made object, has been flying since 1977 and is still inside the Solar System, in the Oort cloud. Step up, the nearest star. Proxima Centauri is 4.24 light-years away. That's 40 trillion kilometers. If Voyager were flying to it, it would take 73,000 years. Step up, the Milky Way, our galaxy. Diameter about 100,000 light-years. Contains 200 to 400 billion stars. The Sun is located about halfway along the radius, in one of the spiral arms. It orbits the galactic center at a speed of 230 kilometers per second, completing one full revolution in 225 million years, a galactic year. Step up, the local group of galaxies. Includes the Milky Way, Andromeda, and several dozen smaller galaxies. Diameter about 10 million light-years. Andromeda is moving toward us and will collide with the Milky Way in 4 to 5 billion years. This will be a grandiose collision, but so slow that if you watched it in time-lapse, compressing millions of years into seconds, it would look like a dance of two ghosts passing through each other. Step up, the Virgo supercluster. Contains the local group and about 100 other groups and galaxy clusters. Diameter about 110 million light-years. The center of the cluster is the giant Virgo cluster, containing thousands of galaxies. But wait. Very recently, in 2014, astronomers realized we belong to an even larger structure. Step up, Laniakea. Immeasurable heavens, in Hawaiian. This is our true galactic neighborhood. The Laniakea supercluster contains about 100,000 galaxies, stretched over 520 million light-years. All these galaxies move toward a common center of attraction called the Great Attractor. The Great Attractor is one of the greatest mysteries of cosmology. It's a region of space with an anomalously high concentration of mass that attracts entire galaxy clusters. We cannot directly observe it because it's located behind the plane of the Milky Way, where dust and stars of our own galaxy block the view. But we know it's there by how galaxies move. Our galaxy, together with the entire local group, with the entire Virgo supercluster, is moving toward the Great Attractor at a speed of about 600 kilometers per second. Step up, the cosmic web. On the largest scales, the universe isn't uniform. Galaxies and galaxy clusters form filaments and walls, separated by enormous voids. It's like foam, the bubble films contain matter, and inside the bubbles there's almost nothing. These filaments stretch for hundreds of millions and billions of light-years. The largest known structures in the universe, such as the Hercules Corona Borealis Great Wall, have a size of more than 10 billion light-years. And finally, the last step up, the observable universe. Diameter 93 billion light-years. Everything we can see. Everything any observer can see, wherever they might be. Beyond its boundaries. Perhaps more space. Perhaps infinity. Let's try to visualize this differently. Imagine we shrink the universe so that Earth becomes the size of a grain of sand. In this scale, the Moon is a few centimeters away, the Sun is a ball the size of a large orange 11 meters from Earth, Jupiter is 60 meters away, Neptune is 350 meters away, Proxima Centauri, the nearest star, is 3,100 kilometers away, the Milky Way is a disk 73 million kilometers in diameter, Andromeda is 18 million kilometers away. The observable universe is a sphere with a radius of 3.4 billion kilometers. And even in this unimaginably reduced scale, the observable universe is larger than the distance from the Sun to Uranus in reality. We live in a space so enormous that any attempts to comprehend it are doomed to failure. Our brain simply isn't adapted for this. We evolved to understand distances from tree to tree, from hill to hill, from village to village. The cosmos mocks our intuition. We've discussed the size of the universe, the speed of its expansion, the conflict between measurements. But all this time we've been skirting the strangest part of the story. We don't know what the universe is made of. Stars, planets, gas, dust, ourselves, everything that consists of atoms, is only 5% of the contents of the cosmos. 5%. The rest is dark matter and dark energy. And we don't know what they are. Dark matter is something that creates gravity but doesn't emit light. We cannot see it. We cannot catch it. We cannot interact with it directly. Except through gravity. We know it exists because we see its gravitational effects. Galaxies rotate too fast, they should fly apart if they contained only visible matter. Galaxy clusters are too heavy. Light from distant quasars bends, passing near massive objects we don't see. Dark matter forms gravitational scaffolds on which galaxies grow. It shapes the large-scale structure of the universe. Without it, the cosmos would look completely different. It accounts for 27% of the mass energy of the universe. But what is it? Some unknown particles. Some form of matter that doesn't interact with electromagnetic radiation. Or maybe it's not matter at all, but a manifestation of us misunderstanding gravity. Physicists have been searching for dark matter for decades. Building detectors deep underground, protected from cosmic rays. Accelerating particles in colliders, trying to create dark matter particles. Observing galaxies, mapping its distribution. So far, nothing. Dark matter remains a mystery. If dark matter is mysterious, then dark energy is a real phantasmagoria. It constitutes 68% of the universe. It's the dominant component of the cosmos. And we absolutely don't understand what it is. Dark energy does something that seems illogical. It causes the universe to expand with acceleration. Gravity pulls things toward each other, slowing expansion. But dark energy works the opposite way. It tears space from within, accelerating expansion. This discovery was made in the late 1990s when astronomers studied distant supernovae. They expected to see that the universe's expansion was slowing under the influence of gravity. Instead, they found it was accelerating. This was so unexpected that the first reaction was, we messed up the calculations. But rechecks confirmed the result. The universe really is accelerating. They gave a Nobel Prize for this discovery. But they gave the prize not for understanding dark energy, but simply for detecting the acceleration. Understanding still doesn't exist. What could this be? The simplest explanation is the cosmological constant, introduced by Einstein. This is a property of space itself. Each cubic meter of vacuum contains a certain energy density. And when space expands, more vacuum is created, meaning more dark energy. This is positive feedback that accelerates expansion. But there's a problem. When physicists try to calculate the magnitude of the cosmological constant from fundamental principles, they get a number that's larger than observed by a factor of 10 to 120. This isn't a typo. 10 to the 120th power. 1 with 120 zeros. This is the worst prediction in the history of physics. A discrepancy between theory and observation of 120 orders of magnitude. Either we fundamentally misunderstand quantum physics, or something incredibly subtle reduces the cosmological constant to almost zero, but not quite. This is called the cosmological constant problem, and it's one of the deepest mysteries of modern physics. Alternative explanations of dark energy include various exotic fields and particles. Maybe it's not a constant but a changing quantity, quintessence, a scalar field that evolves over time. And here's where everything ties back to the Hubble tension. Because if dark energy isn't constant, if it changes, this directly affects the rate of the universe's expansion. This could explain why local measurements give one number and predictions from the early universe give another. Some recent data from the Dark Energy Spectroscopic Instrument, DESI, hint at exactly this. Dark energy may be changing over time. If this is confirmed, it's a revolution. It means the fate of the universe isn't determined. We don't know whether it will expand forever, or expansion will someday stop, or acceleration will become so strong that the universe will tear itself apart in a big rip. Let's do this once more. 95% of the universe consists of things we don't understand. Dark matter. Dark energy. Invisible, intangible, incomprehensible. All our science, all our knowledge, all our civilization is based on studying 5% of reality. The rest is terra incognita. Uncharted land. Imagine you're studying an ecosystem but can see only 5% of living organisms. You see some large animals but don't see plants, insects, microorganisms. Can you truly understand how the ecosystem works? This is where we are with the universe. We see stars and galaxies, but they're just foam on the surface of an ocean of invisible reality. And yet, despite this fundamental ignorance, we try to measure the universe. Determine its size. Understand its evolution. Predict its fate. Is it surprising that we encounter paradoxes? That the numbers don't add up? That theory and observations conflict? Maybe the real miracle is that we're capable of understanding anything at all. There are things we might someday know. And there are things we can never know, even in principle. Cosmology faces both kinds of limits. The particle horizon is a fundamental limit of observability. It's the boundary beyond which events cannot affect us because even light won't have time to reach us in the entire lifetime of the universe. Once this horizon was close. In the first moments after the Big Bang, the observable universe was tiny. Then it grew as light traveled farther and farther. But here's the paradox: although over time light manages to travel a greater distance, the particle horizon doesn't necessarily increase. Why? Because space is expanding. Imagine you're running toward the horizon, but the ground under you is also moving, carrying the horizon away. If the ground is moving away faster than you're running, you'll never reach the horizon. Moreover, the horizon may move away from you. The same with the cosmic horizon. Distant galaxies are receding due to the expansion of space. And if they're receding faster than the speed of light, which is possible because it's not them moving but space between us expanding, we'll never see them. Moreover, due to accelerated expansion caused by dark energy, the particle horizon in the future will shrink. Galaxies we see today will disappear beyond the horizon in billions of years. Their light will cease to reach us. Future civilizations, if they arise trillions of years from now, will see a completely different cosmos. They'll see only their local group of galaxies, the rest of the universe will hide beyond the horizon. They won't see the cosmic microwave background, it will stretch and weaken to indistinguishability. They won't be able to detect the universe's expansion. For them, cosmology will be impossible. They'll think they live in a static, limited universe consisting only of their galaxy. We see much more because we live at a special time. 100 billion years after the Big Bang, accelerated expansion will erase most cosmological evidence. We see the universe in its youth, when it's still ready to reveal its secrets. This is luck. Or maybe it's not luck but inevitability. Intelligent life can only arise in the era when the universe is old enough for the formation of heavy elements but still young enough to be observable. Besides physical horizons, there are also conceptual boundaries of our understanding. We try to understand the universe using physics. But physics is a language we invented. It's a mathematical structure we built to describe observations. How universal is this language? How accurately does it reflect reality? Maybe the universe is structured in ways that are in principle impossible to describe with mathematics. Or at least with the mathematics we know. Philosopher Thomas Nagel once wrote an essay, "What is it like to be a bat?" His argument was this: a bat perceives the world through echolocation. Its conscious experience is fundamentally different from ours. And we cannot truly understand what it's like to be a bat because we don't have access to that experience. Maybe the same is true for the universe. Maybe there are aspects of reality we cannot grasp in principle because our brain, our mathematics, our physics, all of this is a product of evolution in certain conditions on a small planet. We evolved to understand trajectories of thrown stones, plant growth, animal behavior. Not to understand quantum mechanics, space-time curvature, or the nature of dark energy. Nevertheless, amazingly, our physics works. It makes predictions. These predictions come true. We built an entire technological civilization on this foundation. But maybe we're working within a limited domain of applicability. Maybe our physics is a local approximation that works well at our scale of energies and distances but breaks down at the largest or smallest scales. The Hubble tension may be a signal of exactly this: we've reached the limit of applicability of our theories. Beyond that, there be dragons. Cosmologists aren't giving up. Around the world, in orbit and on Earth, an army of telescopes works, each trying to contribute to solving the puzzle. The James Webb Telescope continues observations. New data arrives every week. It looks farther and farther, studying galaxies on the edge of the observable universe, galaxies that were born when the cosmos was very young. These observations have dual significance. First, they help refine the cosmic distance ladder, adding new rungs, new calibrations. Second, they allow studying the early universe directly, comparing what we see with what the model predicts. The Nancy Grace Roman Telescope, scheduled to launch by 2027, promises to revolutionize cosmology. Its wide field of view will allow studying millions of galaxies simultaneously. It will search for gravitationally lensed supernovae, a phenomenon where light from an exploding star is bent by the gravity of an intermediate galaxy, creating multiple images. These multiple images appear at different times, with delays from hours to years. By measuring this delay, distances can be calculated geometrically, independently of the cosmic distance ladder. This is a completely new method of measuring the Hubble constant that doesn't depend on either Cepheids or cosmic microwave background. Roman may discover hundreds of such lensed supernovae. If lucky, this will give an independent measurement of the Hubble constant and possibly indicate where exactly the problem lies. On Earth, new giant telescopes are being built. The Extremely Large Telescope, ELT, in Chile with a mirror 39 meters in diameter. The Giant Magellan Telescope, GMT, with an effective mirror of 24 meters. The 30-meter telescope, TMT, in Hawaii. These leviathans will see the universe with unprecedented detail. They'll be able to study exoplanet atmospheres, look at the first stars, map the distribution of dark matter. And perhaps they'll help resolve the Hubble tension. Parallel to astronomical observations, ground-based experiments proceed. Gravitational wave detectors like LIGO and Virgo have opened a new window into the universe. Gravitational waves are ripples in spacetime created by cataclysmic events like black hole mergers. These waves travel at the speed of light, carrying information about the events that generated them. And, critically important, they allow measuring distances directly. When two neutron stars merge, they emit both gravitational waves and light. Gravitational waves tell us how massive the stars are and how far away they are. Light tells us how fast their galaxy is receding. Combining this data, the Hubble constant can be calculated. This is another independent method, the so-called standard siren, by analogy with standard candles. So far there are few such observations, several events. Precision is insufficient. But with each year there are more detectors, they become more sensitive, the number of detections grows. In 10 years, third-generation detectors like the Laser Interferometer Space Antenna, LISA, will begin operating. They'll detect hundreds and thousands of events. This will give statistics sufficient for precise measurements. Maybe gravitational waves will give us the answer. Or maybe the answer will come from an unexpected direction. From experiments searching for dark matter. From observations of cosmic rays. From studying neutrinos. Science isn't linear. Breakthroughs often come from where they weren't expected. Let's pause for a moment. We've discussed measurements, telescopes, paradoxes, dark matter, expansion. But behind all these technical details it's easy to lose the forest for the trees. Let's return to the simple fact, the universe is huge. So huge that this hugeness breaks our minds. What does this mean for us? For humanity? For the meaning of our existence? There are two extreme reactions. One is nihilism. We're so small, so insignificant on the scales of the cosmos, that our lives have no meaning. All our sufferings, joys, achievements, tragedies, all of this is less than a speck of dust in an ocean. Even if humanity disappears tomorrow, the universe won't notice. Even if the solar system evaporates, the cosmos will remain indifferent. The other reaction is awe. We're part of this magnificent cosmos. We're the universe's way of knowing itself. From the chaos of the Big Bang, through billions of years of evolution of stars and galaxies, atoms arose, then molecules, cells, organisms, consciousness. And now this consciousness looks at the universe and tries to understand it. We're carbon, oxygen, nitrogen, all the heavy elements in our bodies were born in the cores of stars. Once these atoms were part of a stellar core, where thermonuclear fusion turned light elements into heavy ones. Then the star exploded, scattering these atoms into space. They became part of a gas cloud that compressed into a new star, our Sun, and planets around it. And then these atoms became part of living organisms, became us. We're stardust that learned to think. We're the cosmos looking at itself. This isn't a poetic metaphor. This is a literal fact. There's another perspective, simultaneously frightening and profound. It's called the anthropic principle. The universe we live in possesses certain properties. The constants of nature have certain values. Particle masses are what they are. The strength of gravity is what it is. And it turns out these values are incredibly finely tuned for the existence of life. Change any fundamental constant even by a few %, and life becomes impossible. Make gravity slightly stronger, stars will burn too quickly, not having time to spawn planets. Make it slightly weaker, stars won't be able to ignite at all. Change the electron's mass, hydrogen atoms will become unstable. All chemistry will collapse. Make the strong nuclear interaction slightly different, thermonuclear fusion in stars won't be able to produce carbon, oxygen, and other elements necessary for life. There are many examples. The universe seems tuned for our existence with incredible precision. The probability of randomly hitting such a combination of parameters is negligibly small. How to explain this? One answer is religious or teleological: the universe was created specifically for life. There's design, purpose. Another answer is the anthropic principle: we observe a universe with such properties precisely because only in such a universe can observers exist. This is a form of selection effect. If there are many universes with different constants, multiverse, we'll inevitably find ourselves in one where life is possible, because in other universes there would be no one to ask questions. This isn't an explanation in the usual sense. It's rather an acknowledgement that some questions have tautological answers. We're here because we can be here. In the context of the universe's size, an inevitable question arises: are we alone? If the universe contains trillions of galaxies, each with billions of stars, many of which have planets, then statistically it seems incredible that life arose only on Earth. And yet we don't see any signs of other civilizations. The sky is silent. This is the Fermi paradox: where is everybody? Maybe life is incredibly rare. Maybe intelligent life is even rarer. Maybe technological civilizations tend to self-destruct shortly after developing nuclear weapons or artificial intelligence. Or maybe interstellar distances are simply too great. Even if there are thousands of civilizations in our galaxy, the average distance between them might be thousands of light years. Communication becomes practically impossible. Travel, even more so. Imagine two villages separated by an ocean, in an era when there are no ships. Each village might believe it's alone in the world because the ocean is insurmountable. The same with civilizations in space. The ocean of spacetime separates us. Maybe the galaxy is full of life, but all this life is isolated. Confined to its little islands, having no way to connect. Or maybe, And this is the creepiest possibility: we really are alone. Maybe life is so improbable that even in a universe with trillions of galaxies it arose only once. Only here. Only us. In that case, cosmic responsibility lies on us. We're the only way the universe can know itself. If we disappear, the light of consciousness will go out throughout the cosmos. Forever. The size of the universe and the speed of its expansion determine its fate. Let's look into the future, the distant future, when stars go out, galaxies disperse, and time itself loses meaning. There are several scenarios for the end of the universe, depending on the nature of dark energy. If dark energy is constant, the cosmological constant, the universe will expand forever, and expansion will accelerate. Galaxies will move away from each other faster and faster. In a few tens of billions of years, most galaxies will disappear beyond the event horizon. The local group of galaxies, the Milky Way, Andromeda, and a few others, will remain gravitationally bound and eventually merge into one giant galaxy. But around there will be emptiness. Absolute, impenetrable emptiness. The cosmic microwave background will stretch to infinite wavelength and become indistinguishable. The cosmos will become completely black. In 1 trillion years, star formation will end. All interstellar gas will be exhausted. The last stars will go out in hundreds of trillions of years. Only cold remnants will remain: white dwarfs, neutron stars, black holes. In 10 to 20 years, planets will fall onto their dead stars or be ejected into interstellar space. In 10 to 40 years, galaxies will decay. Stars will be thrown into the void or absorbed by black holes. In 10 to 100 years, even black holes will evaporate through Hawking radiation. Only rarefied gas from the rarest particles, photons with infinitely long wavelengths, and emptiness will remain. This is the end. Heat death. Maximum entropy. Nothing happens, and nothing will ever happen again. If dark energy isn't constant and can become negative in the future, or if it doesn't exist at all and expansion will someday slow due to gravity, then another finale is possible. Expansion will stop. Then the universe will begin to contract. Galaxies will start converging. The cosmic microwave background, instead of stretching and cooling, will begin to compress and heat up. In billions of years, galaxies will start colliding. The sky will light up from thousands of collisions. In tens of billions of years, all the universe's matter will merge into a single mass. Temperature will rise. Stars will evaporate. Atoms will break down into elementary particles. The universe will become like what it was in the first moments after the Big Bang, only in reverse sequence. Eventually everything will collapse into a singularity, the Big Crunch, mirror reflection of the Big Bang. Maybe this collapse will spawn a new Big Bang, a new universe. A cyclic cosmos, dying and being reborn eternally. The scariest scenario. If dark energy isn't constant but grows over time, the acceleration of expansion will intensify. First, this will lead to standard heat death, but then acceleration will become so strong that it will start tearing structures from within. In a few tens of billions of years, galaxy clusters will be torn apart. In hundreds of billions, individual galaxies. In 1 trillion years, planetary systems. Earth will be torn away from the Sun. Then expansion will become so rapid that it will tear planets apart. Then, molecules. Then, atoms. Eventually even space-time will tear to pieces. The Big Rip. This is the end not only of matter but of space and time themselves. Complete, total annihilation. Which of these scenarios awaits our universe? It depends on the nature of dark energy. And that's why measurements of the Hubble constant and understanding expansion are so important. Current data point to heat death as the most likely scenario. The universe, it seems, will expand forever, cooling, emptying, dying a slow death of maximum entropy. But recent hints of dark energy variability from DESI introduce uncertainty. If dark energy really changes, the future becomes less predictable. The Hubble tension also plays a role. If local expansion really is faster than the model predicts, this could mean acceleration is stronger than we thought. This shifts us toward the Big Rip. The fate of all existence hangs on numbers we're still trying to measure accurately. We live in a space so vast that the word vast loses meaning. In a universe that may be infinite, that may contain infinite copies of ourselves, infinite other worlds. We observe it with instruments that see billions of light years, that look billions of years into the past. We measure it with precision that would have been unthinkable a generation ago. And we discover that we don't understand it. That our best theories don't match observations. That the universe is expanding at two different rates simultaneously, depending on how we measure. This contradiction isn't a failure. It's an opportunity. An invitation to go further, to think deeper, to build new theories. Perhaps we stand on the threshold of a revolution in physics comparable to the one Einstein made a century ago. Or perhaps the answer is simpler than we think. Perhaps there's some subtle effect, some overlooked detail that will explain everything once we find it. We don't know. That's the beautiful part. That's what drives science forward, not knowing, but seeking. The universe measured its own size through us. Through creatures made of stardust, evolved on a tiny planet, capable of building telescopes and writing equations. And the universe discovered that it's bigger than its own measurements. That it contains mysteries even it doesn't understand. Maybe that's the real answer. Not a number. Not a theory. But the recognition that reality is stranger, deeper, more wonderful than we can ever fully comprehend. That every answer opens new questions. That the horizon of knowledge always recedes as we approach it. We measured the universe. And in measuring it, we discovered how little we know. How vast is our ignorance compared to the vastness of space. Perhaps this is the most important measurement of all.